Here we go. The normal force question. There are variations of this. This is just one of them, but this is a good one. Just going to make it a little bigger. Okay, here it is. If you had a box and you needed to push it along the ground, you would have to push with a force that exceeds the force of friction. If you didn't, the box wouldn't move. So that's what we're going to do. We're going to push a box right here. But the box, like many boxes that you encounter now in your life, are smaller. Or you've grown. They're not big anymore. And you have to stoop down low and push this box like this. So really what you're doing, I'll just make this a little bit bigger. You're pushing on the box downward as well as to the right. So the box is actually feeling heavier on the floor as well as getting pushed to the right. This is level ground right here. There are other forces acting on this box. The box has a weight, and the weight of the box pushes down on the ground. In fact, the weight of the box pushes down like this. And equal and opposite to the weight, because it's not on a slope, is the normal force. So here's the normal force. Usually, it's equal to, but opposite the weight. But this time, the normal force doesn't equal the weight. And the reason for that is, this normal force, the floor has to hold the box up, its weight, but also the pushing down force that you're giving it. And if you don't believe me, just lean over to your partner, push them on their chair down. They feel heavier, but they're not. They feel heavier because you're pushing down on them too, okay? So there's one other force. What is it, you guys? What's the other force? Friction. Right here. Friction. Okay, weight is gravity. So someone said weight, you're right, but it's already covered. So we've got all the forces acting on this box, okay? And some of them acting from the box. I've got an angle. I need to give you some information. This is 30 degrees, we'll say. And I will also say that the F push. What's that? 250 newtons. And I'll say that the mass of the box is 11 kilograms, okay? Thanks. And there's one other thing. The force of friction comes from a coefficient of friction of 0.25 between the ground and the box. I'm trying to write big so that it shows up on the video a little bit better. So we've got all the forces, and you could probably imagine what the question is. What is the acceleration of the box when you push it, okay? So here's the question. What is the acceleration of the box as it is pushed? Okay, just want to redraw the free body diagram of the box, the diagram of the forces, and just simplify it a bit. So free body diagram of the box. So it's the forces on the box. That's what the free body diagram means. So I'll draw the ground again. And here's the box in red. Right here. And here are the forces again. So nothing but forces. There's that one right here. And there's the force of friction right here. The green one is the pushing force. And then, like I said, there's the weight down, but then the normal force back up. So this one right here is the normal force. And it comes partially from this weight down, okay? Normal force is always normal or perpendicular to the surface. So if it was a curved surface, the normal force would be perpendicular to that surface as well. Okay. But you're right, it's always perpendicular to the surface, or normal. Normal means 90 degrees, okay? If you draw a normal of something in geometry, it means it's 90 degrees. They could say, draw the perpendicular. It would be the same thing. Okay, so what I need to do is realize which two forces are tugging at each other. There are a couple. We want it to move in this direction, the box. We want it to move to the right. So there really is a component of the pushing force going that way. That's the one we want to know. This one's called F parallel to the surface. It's parallel to it. And then there's F perpendicular right here. And then we have the angle 30 degrees. So the winning force, we think, if it's going to move at all, the winning force has to be F parallel. The losing force is force of friction. So really, the theory that we are working on is Newton's second law. Winning force minus losing force equals ma. And that winning force is F parallel. The losing force is force of friction. And that equals the mass times the acceleration. Okay. So that is what we have to solve for. So it's winning force minus losing force equals m times a. And now we just have to find out what F parallel is and force of friction is, and then it'll work out just fine. Parallel force. This one right here, the green one. I need to find it. And that's not too hard. Did I tell you what the push force was? Nice. So find F parallel. And to do that, you just go sine would be opposite over hypotenuse. That's not going to help. Cos 30 is going to help. So cos 30 degrees is equal to adjacent F parallel over the hypotenuse, which is the F push. And we want to find F parallel, so it's just cos 30 degrees times F push is equal to F parallel. And then just put in the numbers. Cos 30. F push was 250. And that does equal F parallel. And what do you guys get when you calculate that number?
260.5.
Great. And anybody else too?
Yeah.
Nice. 216.5. Just a bit. We'll keep digits. I'd like to keep 3 or 4 and then round up to 2 or 3 later on, okay? This is newtons. So we've got the winning force. Now to find the losing force. Find force of friction. Remember, force of friction is equal to mu times F normal. Not weight, but F normal. F normal in this case is not the weight. F normal is, take a look at the diagram here. It is. Just like when you guys were in the elevator going upward, you felt your weight and there was some extra push or tug downward. Here, someone's actually pushing downward onto the box as well as the weight of the box. So the normal force is a F perpendicular plus the weight. Okay? So this one plus that one has to equal this one, the normal force. So I'm just going to replace that here. Mu times the weight plus F perpendicular. And then just put the rest of the numbers in. Mu is 0. What was it? 25? Nice. Times weight is whatever the thing weighed. 11 times 9.8. Not just 11, but 11 times 9.8. It's got to be a weight, not a mass. And then F perpendicular, by the same sort of process as we did here, it would be 250 times sine 30. We did, yes. Did you get it answered yet, though? Like, do you have an answer for it? Could you? That'd be great. So we need to know what this thing is. What'd you get? Anybody else? Go ahead. Great. Nice. Thanks.
I said it out loud, it was wrong.
It's not so bad after Tyrell's already said it, though. It helps a lot. Okay, and that's what they got the last class, too. So we have the winning force and we have the losing force. This is a long way around to find the losing force, but it's what you have to do, okay? It's not as simple as it was last year. So back to F net equals M times A. The winning force was force in the parallel direction. Losing force was force of friction. And the force that's winning was 216.5. The losing force you just calculated is 58.2. And that equals M times A. M you already know, it's 11 times the acceleration you're looking for. And you just do your algebra and you get what your answer is. And what do you guys get? Nice. Pretty big acceleration, but given the numbers in this problem, that's what it is. Okay, so that is what the acceleration, I should say, is. Okay, everyone okay with that? A little bit more involved than last year. 14.4. Oh, 14.4. Okay, sounds good. Thanks. 14.39, I think. Okay, good work.
Thank you.